the universe will die. Every equation in physics points to the same conclusion. Every observation we've made confirms it. But cosmologists lose sleep over one troubling question. We don't actually know how it will happen. A sudden violent end, a slow fade into darkness, or something far more terrifying that might already be underway. Over the next 2 hours, we're walking through 3 scientifically validated scenarios for the death of reality itself. One of them could begin at any moment. Let's explore the most disturbing possibility first. As you're listening right now, the universe races toward its doom. 3 fundamental forces battle for control of everything that exists. Gravity pulls matter together. Dark energy tears space apart. Entropy drives everything toward disorder. Only one force will win. The clock already counts down, though we can't see the numbers. Some scenarios give us trillions of years to prepare. Others might leave us with minutes. I'm going to show you exactly what the end looks like. We'll start with the death that arrives last but never ends. Scientists call it heat death. Picture the universe fading away with an infinite whimper, rather than any kind of bang. A cosmic retirement home where the last stars flicker out, the final black holes evaporate, and what remains becomes a cold, dark ocean stretching forever. Time itself loses meaning in this scenario because nothing ever changes again. Nothing can change. There's no energy left to power any process, any thought, any movement, just endless night. To understand how we reach this frozen eternity, we need to fast forward far beyond anything humans can easily imagine. 100 trillion years from now, the scale of that number defies comprehension. If you squeezed our entire cosmic history into a single calendar year, with the Big Bang happening on January 1st, and today somewhere around December 31st, then 100 trillion years would stretch across roughly 7,000 more of those calendars. Every star you can see tonight will be dead, gone, consumed. The Milky Way will have collided with Andromeda and several neighboring galaxies, forming a massive elliptical structure. Even that supergalaxy will sit mostly dark. Star formation needs gas clouds, and by this distant epoch, nearly all the hydrogen fuel will have been burned through. The last generation of stars will be small, dim red dwarfs, slowly consuming whatever scraps of fuel remain. These red dwarfs function as the marathon runners of stellar evolution. While massive blue giants burn brilliantly and collapse after just a few million years, red dwarfs can survive for 10 trillion years or longer. They're incredibly miserly with their fuel, converting hydrogen to helium at an agonizingly slow rate. As the cosmos ages, these become the only light sources. Imagine a galaxy containing billions of solar systems, but only a handful of faint red stars scattered across impossible distances. The space between them, once bright with newborn suns, sits empty and cold. Each star becomes a lonely lighthouse in an expanding ocean of darkness. Even these patient stars can't last indefinitely. One by one, they'll exhaust their fuel reserves. When a red dwarf finally dies, it doesn't explode like its massive cousins. It simply stops. The fusion reactions in its core sputter out. The star collapses into a white dwarf, a dense ember roughly the size of Earth, but packing the mass of a sun. White dwarfs don't generate fresh energy. They just radiate away the heat they accumulated during their lives. Slowly, unbelievably slowly. A white dwarf can take a quadrillion years to cool completely, but eventually it will. Every white dwarf becomes a black dwarf, a cold, dark sphere of carbon and oxygen drifting through space, a stellar corpse. By 10 to the 40th power years in the future, a number so large it practically erases human intuition. All the stars are dead, every single one. The universe has become a graveyard. But the graveyard isn't empty. Scattered throughout the darkness are planets, asteroids, dead stars, and something far more ominous, black holes. These gravitational predators have been busy. Over the trillions of years, they've been consuming everything that wanders too close. Rogue planets, dead stars, gas clouds, even photons. Black holes represent the ultimate predators, and in this dying universe, they're the last entities with any significant energy reserves. The story takes a strange turn here. For most of cosmic history, physicists assumed black holes were eternal. Once something crossed the event horizon, that boundary of no return, it was gone forever. The black hole would just continue growing, accumulating mass, becoming more powerful. Then, in 1974, a young physicist named Stephen Hawking discovered something that shocked everyone. Black holes aren't eternal, they evaporate. Through a bizarre quantum mechanical process now called Hawking radiation, black holes slowly leak energy. Particle-antiparticle pairs spontaneously form at the edge of the event horizon. Usually they annihilate each other instantly, but occasionally one particle falls into the black hole while the other escapes into space. To any outside observer, the black hole appears to be radiating particles. Every particle that escapes carries away a tiny fragment of the black hole's mass. For a black hole with the mass of our Sun, this process happens absurdly slowly. Complete evaporation would take 10 to the 67th power years. That's a 1 followed by 67 zeros. A number so vast that if you started counting atoms in the observable universe, you'd run out long before reaching it. But black holes have nothing except time. In this dead universe with no stars, no planets harboring life, no events of any significance, the black holes simply exist in the darkness, slowly, imperceptibly, shrinking. Imagine you could observe this process. For eons beyond measure, nothing happens. The black hole just exists as a spherical region of warped space-time floating in the void. Then, after timescales that dwarf our universe's current age by factors we can barely express mathematically, the black hole starts to shrink noticeably. As it loses mass, something counterintuitive occurs. It gets hotter. Smaller black holes radiate more intensely than large ones. As the black hole approaches the end of its existence, it begins to glow, first dimly, then brighter. In its final moments, a black hole releases all its remaining energy in a tremendous burst of radiation. For just an instant, this dying monster outshines anything else in the dead universe. A final scream into the void, then silence. The black hole is gone, converted entirely into radiation, into photons that will travel through space until the end of time itself. But here's the truly haunting part. Even the smallest black hole takes incomprehensible time to evaporate. A supermassive black hole, like the one at the center of our galaxy containing millions of solar masses, that would take 10 to the 100th power years to disappear. A Google of years. Written out, that's a 1 with 100 zeros after it. There's no meaningful way to comprehend this timescale. Our universe currently sits at only about 14 billion years old. A Google years is so much longer that our universe's current age is less than a rounding error. But even a Google years will eventually pass. When the last black hole in the universe evaporates, when that final flash of Hawking radiation dissipates into the darkness, what remains? Photons, electrons, positrons, neutrinos, all the fundamental particles spread across a volume of space that has expanded to unimaginable dimensions. The universe at this stage is incomprehensibly vast and incomprehensibly empty. The distance between any two particles gets measured in scales we don't even have names for. And here's the crucial point. All these particles exist at the same temperature. The universe has reached maximum entropy. Heat death has arrived. In thermodynamics, entropy measures disorder, how spread out and uniform energy has become. The second law of thermodynamics states that entropy always increases in a closed system. You can't uncook an egg, you can't unburn wood. Energy flows from hot regions to cold regions until everything reaches the same temperature, and then nothing else can happen. All work, all processes, all change requires a temperature difference, a gradient that energy can flow down. In a universe at maximum entropy, no gradients remain, no hills for energy to roll down. Everything is flat, uniform, utterly still. Temperature becomes meaningless because temperature just represents the average kinetic energy of particles. And when particles are separated by distances larger than galaxies, larger than superclusters, so far apart that they will never interact again, what does temperature even mean? Time also loses meaning. Time, as we experience it, represents the progression of events, of change. In a maximum entropy universe, nothing changes. Nothing can change. There's no energy available to power any process. A particle might drift through space for trillions upon trillions of years without encountering another particle. And even if two particles did somehow meet, they wouldn't have the energy to interact in any meaningful way. Here we find the true horror of heat death. The end lacks drama. There's no explosion, no violent finale. The universe doesn't die screaming. It dies whispering, fading away into a cold, dark, featureless void that lasts forever. Forever, actually, eternally forever. Because in this state, there's no mechanism for anything new to happen, no way to restart, no escape, just an infinite expanse of near absolute zero space with occasional particles drifting in the darkness, separated by distances so vast they might as well be alone in their own private universes. What makes this scenario particularly unsettling from a philosophical standpoint deserves examination. Everything that ever happened, every thought ever thought, every feeling ever felt, every civilization that ever existed, every work of art, every scientific discovery, every moment of joy or suffering, all of it leads to this, an eternal state of absolute nothing. All the complexity that emerged over billions of years, all the structure from atoms to molecules to cells to organisms to planets to solar systems to galaxies, all of it breaks down, decays, and dissolves back into the simplest possible state, uniformity, and it stays that way forever. Some physicists have speculated about whether quantum fluctuations might, over truly incomprehensible timescales, spontaneously create new structures. Maybe, they argue, if you wait long enough, even in a maximum entropy universe, Random fluctuations could create a new Big Bang, a new universe. The timescales involved would be 10 to the 10 to the 50 power years or more. Numbers so large they can't be written without exponential notation. But even these speculations remain controversial. Most physicists think that once heat death occurs, that's the end, the final curtain, the cessation of anything happening at all. The universe becomes a static, unchanging void. What if I told you that heat death might actually be the merciful option? Another scenario exists where the universe doesn't slowly fade, but instead tears itself apart, where space itself rips open, shredding galaxies, stars, planets, atoms, and eventually even the fabric of reality. Scientists call this the Big Rip, and unlike heat death, which takes an eternity, the Big Rip happens fast, cosmically speaking anyway. Let me take you through what might be the most violent end imaginable. Right now, our universe is expanding. Galaxies are moving away from each other, and the space between them grows larger every second. We've known this since Edwin Hubble's observations in the 1920s. But here's what changed everything. In 1998, two independent teams of astronomers made a discovery that earned them the Nobel Prize and fundamentally altered our understanding of cosmic fate. They found that the universe's expansion is accelerating, speeding up. Galaxies aren't just drifting apart, they're being pushed apart by something we can barely comprehend. We call it dark energy, and it makes up roughly 70% of everything that exists. We don't know what it is. We can't see it, touch it, or directly detect it. We only know it exists because we can measure its effects on the expansion of space itself. Think about that for a moment. The dominant component of our universe remains completely mysterious. Dark energy permeates every cubic centimeter of space, and it has a peculiar property. Unlike matter, or even dark matter, which gets diluted as space expands, dark energy maintains constant density. As the universe grows, more dark energy appears to fill the new space. Where does it come from? We have no idea. The leading theory suggests it might be a property of empty space itself, what physicists call vacuum energy. But the mathematics behind this idea produces results that are off by a factor of 10 to the 120th power. That's the worst prediction in the history of physics. So we're left with a puzzle. Something is pushing the universe apart, and we don't understand it. Under most circumstances, this accelerated expansion would eventually lead to heat death. Galaxies would fly apart, stars would die, and we'd end up in that cold, dark, eternal void I described earlier. But there's a twist. Dark energy might not remain constant. The strength of dark energy gets described by something called the equation of state parameter, represented by the letter W. Current observations suggest W equals approximately -1. If W stays at -1 forever, we get heat death. But what if W is actually slightly less than -1? What if dark energy grows stronger over time? Then we get something far more catastrophic. We get the Big Rip. Phantom energy describes dark energy that increases in strength as the universe expands. Instead of maintaining constant density, phantom energy density actually rises. More space means more dark energy, which means even faster expansion, which creates even more space, which generates even more dark energy. A runaway feedback loop. Under these conditions, the expansion doesn't just accelerate, it accelerates exponentially. And when expansion reaches a certain critical rate, something profound happens. Space begins expanding faster than the speed of light. You might think that violates relativity, but it doesn't. Relativity says nothing can move through space faster than light, but space itself can expand at any rate. There's no speed limit on the expansion of the universe. When space expands faster than light, the cosmic horizon starts to shrink. Right now, we can see objects that are roughly 46 billion light-years away in any direction. That's our observable universe, the sphere of space from which light has had time to reach us since the Big Bang. As expansion accelerates under phantom energy, this boundary gets closer. Distant galaxies disappear beyond the horizon, their light unable to reach us anymore. Eventually, even nearby galaxies vanish. Then stars in our own galaxy. The observable universe contracts down to our solar system, then just Earth, then smaller still. But the shrinking horizon represents just the beginning. The real violence starts when expansion becomes so rapid that it overcomes the fundamental forces holding matter together. Let me walk you through the timeline. 200 billion years from now, assuming phantom energy exists and behaves as some models predict, the expansion rate reaches a critical threshold. Galaxies begin to lose their gravitational cohesion. The space between stars within a galaxy expands faster than gravity can hold them together. The Milky Way, a spiral structure that has existed for over 13 billion years, starts to dissolve. Stars drift apart, each becoming an isolated island in an ocean of rapidly expanding space. This process accelerates. What takes billions of years at first happens faster and faster as phantom energy density increases. 60 million years before the end, solar systems fall apart. Planets can no longer maintain their orbits. The gravitational bond between Earth and the Sun gets overwhelmed by the expansion of space itself. Our planet spirals outward, tumbling into the darkness. But there's no time to freeze. The end approaches too quickly. 3 months before the final moment, the forces holding planets together fail. Earth's core, mantle, and crust separate. The planet doesn't explode in any conventional sense. Space between the atoms expands so rapidly that the matter simply comes apart. Mountains, oceans, continents, all of it disperses into fragments that continue to separate. 30 minutes before the end, atoms themselves face destruction. The electromagnetic force that binds electrons to nuclei, one of the strongest forces in nature, gets overpowered by the expansion rate. Electrons tear away from their atoms. But the process doesn't stop there. In the final moments, atomic nuclei break apart. Protons and neutrons, held together by the strong nuclear force, the most powerful force we know, separate. And then, in the last fraction of a second, even protons and neutrons dissolve. Quarks, the fundamental constituents of matter, rip apart. Space expands so violently that the very fabric of space-time itself tears. What happens at that final instant? The mathematics breaks down. Our equations produce infinities, which usually means the theory stops working. Some physicists speculate that space-time might fragment into quantum foam, a seething chaos where conventional notions of space and time cease to apply. Others suggest that the entire universe might reach a state of infinite density and infinite temperature in a singularity, similar to what we think happened at the Big Bang, but in reverse. We genuinely don't know. The Big Rip takes us to the edge of physics, beyond what our current understanding can describe. Here's what makes the Big Rip particularly terrifying from a human perspective. You wouldn't see it coming. Light from distant parts of space would be redshifted beyond detection as space expanded. The visible universe would shrink down to a bubble around you. In the final months, you might notice the stars disappearing, winking out one by one. In the final days, the sun might vanish, leaving Earth in darkness, but you wouldn't have time to experience cold or hunger. In the final minutes, your body would begin to come apart, first at the cellular level, then the molecular level, then atomic. There would be no pain. Your nervous system would disintegrate before it could register anything. You would simply cease to exist, along with everything else, as reality itself tore into pieces. The good news, if we can call it that, is we have no strong evidence that phantom energy exists. Current measurements of dark energy suggest W is very close to -1, which would produce heat death rather than the Big Rip. But our measurements aren't precise enough to rule out the Big Rip entirely. We need W to be greater than -1.1 to avoid this scenario, and our current error bars just barely allow for that possibility. Future observations from next-generation telescopes and surveys will narrow down these measurements. Within the next few decades, we should know whether the Big Rip represents a real threat or merely a theoretical curiosity. Even if the Big Rip awaits us, we have time. Current models suggest it wouldn't occur for at least 100 billion years, and most predictions push it out to 200 billion years or more. That's roughly 14 times the current age of the universe. Plenty of time for humanity, assuming we survive, to develop technologies we can't even imagine today. Maybe we could find a way to leave this universe entirely, to tunnel through to some other region of space-time where phantom energy doesn't dominate. Pure speculation, of course, but the timescales involved allow for possibilities we can't currently envision. Before we move on, I want you to consider something. Both scenarios we've explored so far, heat death and the Big Rip, occur in the distant future, incomprehensibly distant. The human species has only existed for about 300,000 years. Civilization has only existed for about 10,000 years. The idea that we might persist in some form for trillions or hundreds of billions of years requires enormous optimism and perhaps a bit of hubris. These scenarios matter more for what they tell us about the universe than for any practical threat they pose to humanity. We'll be long gone, one way or another, before heat death or the Big Rip arrives. But what if I told you there's a third scenario? One that doesn't require waiting trillions of years. One that could happen tomorrow, or in the next second, or the second after that. One we'd never see coming, never have time to react to, never even know had occurred. This is the vacuum decay scenario, and it's the most unsettling possibility of all because it rests on cutting-edge particle physics and discoveries we've made just in the last few years. On July 4th, 2012, scientists at CERN in Switzerland announced they'd discovered the Higgs boson. This particle had been predicted by theory since the 1960s, and finding it represented a triumph of modern physics. The Higgs boson relates to the Higgs field, a quantum field that permeates all of space and gives particles their mass. Without the Higgs field, electrons, quarks, and all other fundamental particles would be massless and would zip around at the speed of light. Matter as we know it couldn't exist. The discovery of the Higgs boson confirmed that this field is real, but it also revealed revealed something deeply troubling. The mass of the Higgs boson matters a lot. It determines the stability of our universe. Physicists measured it at approximately 125 giga-electron volts, or 125 GeV. When they plugged that number into their equations, something unexpected emerged. At this mass, our universe sits in what's called a metastable state. Imagine a ball sitting in a shallow valley on the side of a mountain. The ball is stable for now, resting at the bottom of the valley. But there's a much deeper valley far below. If the ball could somehow get over the ridge separating these two valleys, it would roll down to the lower one, releasing a tremendous amount of energy in the process. Our universe might be that ball sitting in a false vacuum, with a true vacuum waiting below. Quantum mechanics allows for something called tunneling. In the classical world, objects need enough energy to get over a barrier, but in the quantum realm, particles can sometimes pass through barriers even when they don't have sufficient energy. They tunnel through. The probability of this happening depends on the height and width of the barrier, but it's never exactly zero. Applied to the universe, this means there's some small but non-zero probability that somewhere, at some point, a region of space might quantum tunnel from our false vacuum to the true vacuum. When that happens, a bubble of true vacuum forms and begins expanding at the speed of light. Inside this bubble, the laws of physics are different. The Higgs field has a different value, which means particles have different masses. Chemistry doesn't work the same way. Atomic nuclei might not be stable, stars couldn't form, life would be impossible. But the bubble doesn't care about any of that. It just expands, converting false vacuum to true vacuum, driven by the energy difference between the two states. The bubble wall moves at the speed of light, so you'd never see it approaching. Light from the bubble travels at the same speed as the bubble itself. The wall would simply arrive, and in an instant, everything would change. What would happen to you if you were in the path of a vacuum decay bubble? You'd cease to exist. The atoms in your body would suddenly find themselves governed by different physical laws. The electromagnetic and strong nuclear forces that hold your atoms together would have different strengths. Your atoms would come apart, or perhaps reconfigure into exotic forms of matter that can't support life or consciousness. There would be no warning, no transition period, no pain. One moment you exist, the next moment you don't. The entire Earth, the Sun, the solar system, the galaxy, everything the bubble touches would be transformed or destroyed. Could this happen? The mathematics says yes. The question is how likely it is and how soon it might occur. Physicists have calculated the probability of vacuum decay per cubic meter of space per year. The numbers they get are incredibly small, something like 10 to the negative 100 per cubic meter per year. Across the entire observable universe over its entire lifetime, vacuum decay remains highly unlikely. Some estimates suggest our universe should be stable for at least 10 to the 100 years, far longer than heat death or any other scenario. But these calculations come with enormous uncertainties. We don't fully understand the physics at the energy scales involved. There could be other fields, other particles we haven't discovered yet that modify the picture. Small changes in the Higgs mass or the top quark mass could shift the calculations significantly. What makes this scenario particularly unsettling is the possibility that it's already happened. Somewhere in the universe, far beyond our cosmic horizon, a bubble of true vacuum might have formed billions of years ago. It could be expanding toward us right now, racing across space at light speed. We'd have no way to know until it arrived. The bubble could be seconds away or trillions of years away. We simply can't tell. This creates a peculiar kind of cosmic Russian roulette. Every moment we exist represents another moment the universe didn't decay. But each new moment carries that same tiny but non-zero risk. Some physicists argue we can take comfort in the fact that we're still here. If vacuum decay were highly likely, it probably would have happened already given the age and size of the universe. The anthropic principle suggests that we find ourselves in a stable or at least metastable universe precisely because unstable universes don't last long enough to develop observers. We exist, therefore our universe must be reasonably stable. Others point out that this logic only works if we assume our universe is typical. Maybe we're just lucky. Maybe countless other universes have already succumbed to vacuum decay, and we happen to live in one of the survivors. We have no way to know. There's another layer to the vacuum decay problem that makes it even more unsettling. We might trigger it ourselves. Every time we run a particle accelerator at high energies, we're creating conditions that haven't existed in our corner of the universe since the earliest moments after the Big Bang. The Large Hadron Collider at CERN smashes protons together at energies approaching 14 trillion electron volts. That sounds enormous, and by human standards it is, but cosmic rays hitting Earth's atmosphere regularly achieve energies millions of times higher. Nature has been running these experiments continuously for billions of years without triggering vacuum decay, which suggests we're probably safe. Probably. The word probably appears a lot in discussions of vacuum decay, and that's because we're dealing with quantum probabilities and physics at the edge of our understanding. Some theorists worried before the LHC switched on that the collider might create a microscopic black hole that would swallow the Earth, or trigger a strangelet that would convert all matter to strange quark matter, or nucleate a vacuum decay bubble. A careful analysis showed these risks were negligibly small, far smaller than many natural risks we face every day. The LHC has been running for over a decade now, and we're still here. But the fact that serious physicists had to calculate these probabilities at all shows how little we truly understand about the fundamental nature of our universe. Let me put this in perspective with a thought experiment. Imagine a physicist working at a research facility in the year 2157. Let's call her Dr. Sarah Chen. She's monitoring data from an orbital telescope that specializes in detecting subtle variations in the cosmic microwave background radiation. On March 15th, during a routine shift, she notices something anomalous. In a distant galaxy cluster approximately 2 billion light-years away, several galaxies have simply vanished from the spectrum. Not dimmed, not moved, vanished. The light that should be coming from those galaxies just stops. Dr. Chen runs a diagnostic, assuming equipment malfunction. The systems check out fine. She cross-references with other observatories. They confirm it. Approximately 40 galaxies in that cluster have disappeared over the past 3 months of observations. She runs the calculations, working backward from the light travel time. The galaxies themselves vanished roughly 2 billion years ago, and we're only seeing it now because light takes that long to reach us. But here's what makes her hands shake as she types. The void is growing. The absence spreads through the cluster at a specific rate. When she calculates the expansion velocity, she gets a number that makes her stomach drop. The void expands at exactly the speed of light. She realizes what she's looking at. A vacuum decay bubble. Somewhere in that galaxy cluster 2 billion years ago, a tiny region of space quantum tunneled to the true vacuum state. A bubble formed, and it's been expanding ever since, consuming everything it touches. She runs more calculations, mapping the bubble's trajectory. The cluster sits roughly in the direction of the constellation Pisces from Earth's perspective. The bubble expands in all directions equally. By the time the light from its formation reached Earth, the bubble itself has grown to encompass thousands of galaxies. But it's still 2 billion light-years away. Light from the bubble's edge won't reach our solar system for 2 billion years. 2 billion years. Dr. Chen sits back in her chair. She thinks about her daughter, currently 6 years old, learning to read. She thinks about the human species, which has existed for perhaps 300,000 years and might exist for 300,000 more. 2 billion years exceeds the entire history of multicellular life on Earth. The dinosaurs lived and died. Humans emerged, built civilizations, possibly spread to other stars. 2 billion years of history, art, science, love, struggle, triumph, and tragedy. All of it happens in the safety of the false vacuum, while the bubble of true vacuum races toward us at the speed of light, unstoppable and inevitable. She prepares her report. The discovery will revolutionize cosmology. Humanity finally has empirical evidence of vacuum decay. We know it can happen because it did happen. We know the universe is metastable because we're watching a region of it decay in real time. Well, real time delayed by 2 billion years. And we know our ultimate fate. In 2 billion years, give or take a few million, that bubble will reach the Milky Way. The solar system, Earth, any descendants of humanity that still exist, all of it will be consumed by the bubble wall and transformed into whatever exotic physics governs the true vacuum. How do you process that knowledge? How do you continue with your life, knowing that the universe has an expiration date that you can calculate precisely? Dr. Chen goes home that evening. She picks up her daughter from school. They make dinner together. She reads her a bedtime story about explorers discovering new worlds. As she watches her daughter sleep, Dr. Chen thinks about the bubble, currently racing through space 2 billion light-years away, converting false vacuum to true vacuum, erasing galaxies like chalk marks on a board. And she thinks about the 2 billion years humanity has left. That's enough time, surely, to figure out something, to find a way to survive or escape, or at least to live well, to create meaning, to love each other while we can. This thought experiment illustrates something crucial about vacuum decay. Unlike heat death or the Big Rip, which play out over timescales so vast they're almost abstract, vacuum decay could present a concrete deadline. Unlikely, given the incredibly low probability of vacuum decay occurring anywhere in the observable universe during its entire history, but possible, and that possibility changes the philosophical calculus. When death comes in an incomprehensible future, it's easy to ignore. When death comes with a date on the calendar, even a date billions of years away, it demands a response. But let's return to reality. and what we actually know. The calculations for vacuum decay stability in our universe depend critically on three parameters: the mass of the Higgs boson, the mass of the top quark, and the strong force coupling constant. We've measured the Higgs mass quite precisely at 125.1 GeV. The top quark mass sits at approximately 173 GeV. The strong force coupling constant has been measured through numerous experiments. When you plug these values into the equations of quantum field theory and calculate the effective potential of the Higgs field, you get a curve that shows our current vacuum sitting in a local minimum, but with a lower global minimum at much higher field values. The barrier between these two minima is high but finite. The probability of quantum tunneling through that barrier can be calculated, though with significant uncertainties. Most analyses suggest our vacuum should remain stable for at least 10 to the 100 years, possibly much longer. Some calculations push this out to 10 to the 600 years or beyond. These timescales dwarf everything else we've discussed. Even heat death occurs earlier than this. So in practical terms, vacuum decay probably represents the least immediate of all cosmic threats. The key word, again, being probably. Why do physicists hedge so much on this? Because the calculations involve extrapolating known physics up to energy scales we've never directly tested. The Higgs field equations work perfectly well at the energies we can probe with particle accelerators. But to calculate vacuum stability, we need to know how those equations behave at energies approaching the Planck scale, which is 10 to the 19 GeV. That's a quadrillion times higher than anything we can produce in the LHC. At those energies, we expect quantum gravity effects to become important. We don't have a working theory of quantum gravity, so we're extrapolating equations beyond their known domain of validity and hoping they still work. New physics could change everything. If there are additional Higgs bosons, as some theories predict, they could stabilize the vacuum. If supersymmetry exists, which posits that every known particle has a heavier partner particle, that could also stabilize things. Or new physics could make the vacuum less stable. We simply don't know until we either discover new particles or develop theories that work at those extreme energy scales. This is why particle physics matters for cosmology. The experiments happening in underground labs and particle accelerators around the world are probing the fundamental structure of reality and telling us whether our universe is truly stable or just pretending to be. I want to pause here and zoom out for a moment. We've now walked through three scenarios for the end of the universe. Heat death, where expansion and entropy lead to a cold, dark, eternal void. The Big Rip, where accelerating expansion tears apart galaxies, stars, planets, atoms, and space-time itself. And vacuum decay, where our universe quantum tunnels to a lower energy state, potentially erasing everything in a bubble expanding at light speed. Three very different endings, each based on solid physics, but with different assumptions and uncertainties. Heat death seems most likely given current observations. Dark energy appears to have an equation of state parameter very close to -1, which leads inevitably to heat death over timescales of 10 to the 100 years or more. The Big Rip requires phantom energy, which we have no evidence for, though we can't completely rule it out. Vacuum decay could happen at any time in principle, but the probability is so low that it probably won't occur until long after heat death would have happened anyway. So if you're placing bets on how the universe ends, heat death is the favorite. But here's what's interesting. All three scenarios share a common theme. The universe ends because of the same principle that governs a melting ice cube or a cooling cup of coffee: entropy, the second law of thermodynamics. Systems evolve toward states of higher entropy, toward equilibrium, toward uniformity. The universe started in a very low entropy state at the Big Bang. All the matter and energy packed into an incredibly small, hot, dense region. High energy density, low entropy. Everything that's happened since represents the universe evolving toward higher entropy. Stars form, burn their fuel, and die. Black holes grow and eventually evaporate. Structures emerge and dissolve, and eventually the universe reaches maximum entropy, whether that happens through heat death's endless expansion, the Big Rip's violent tearing, or vacuum decay's transformation. The details differ, but the direction is always the same: toward disorder, toward uniformity, toward the end. This raises profound questions about meaning and purpose. If everything ends, if all our works and days lead ultimately to oblivion, what's the point? Different philosophical traditions answer this differently. Some say the inevitability of ending makes the present moment more precious. If we only have a finite time, we should make it count. Others argue that meaning must be cosmic to be real, that our actions only matter if they have permanent consequences, and if the universe ends, nothing matters. Still, others suggest that meaning exists independent of duration, that a beautiful moment is beautiful whether it lasts a second or a trillion years. I find myself drawn to a perspective articulated by the physicist Sean Carroll. He argues that we should embrace the universe as it is, not as we wish it to be. Yes, the universe will end. Yes, everything we do will eventually fade away, but we exist now, in this brief window of time when the universe has cooled enough to allow complex structures but hasn't yet expanded and cooled so much that nothing interesting can happen. We live in what some cosmologists call the stelliferous era, the age of stars, when the universe is bright and full of energy and possibility. This era represents just a tiny fraction of cosmic history. Before it, the universe was too hot and dense for stars. After it, the universe will be too cold and diffuse. We happen to exist during the interesting part. More than that, we're part of the universe's way of understanding itself. The atoms in your body were forged in stars. The iron in your blood came from a supernova. You are literally made of stardust, as Carl Sagan famously noted. And your consciousness, your ability to think and feel and wonder about cosmology, represents billions of years of evolution and complexity emerging from simpler states. The universe, through you, looks back at itself and asks how it began and how it will end. That seems meaningful to me, even if the answers are uncomfortable. Let me take you deeper into the physics of why the universe must end. There's a beautiful and tragic principle at work here, and it goes back to the very foundations of thermodynamics. In the mid-19th century, a German physicist named Rudolf Clausius formulated what he called the second law of thermodynamics. In its simplest form, it states that heat flows from hot objects to cold objects, never the reverse. You can watch a hot cup of coffee cool down to room temperature, but you'll never see a room temperature cup of coffee spontaneously heat itself up. That seems obvious, but the implications ripple outward to encompass the fate of everything that exists. Clausius introduced the concept of entropy to quantify this principle. Entropy measures the degree of disorder or randomness in a system. High entropy means high disorder. Low entropy means high order and structure. The second law states that in any isolated system, entropy always increases over time. You can decrease entropy locally by doing work, like when you organize a messy room or when a plant grows by absorbing energy from sunlight. But every local decrease in entropy requires an equal or greater increase in entropy somewhere else. The room gets organized, but your body generates heat and uses energy, increasing entropy overall. The plant grows, but the sun burns fuel and radiates heat into space, increasing entropy by far more than the plant decreases it. The universe as a whole represents the ultimate isolated system. There's nothing outside it, no external energy source, no place for entropy to escape, so the universe's total entropy must increase. At the Big Bang, all the matter and energy in the universe occupied an incredibly small volume. You might think that sounds like high entropy, maximum disorder, but actually the opposite holds true. The early universe existed in an extremely low entropy state. Why? Because gravity changes the entropy game. For gravity, clumped matter has lower entropy than spread out matter. A gas cloud collapsing under its own gravity releases energy and increases entropy even though the gas becomes more concentrated and seemingly more ordered. Think about a star like our sun. It formed from a diffuse cloud of hydrogen gas. That cloud collapsed under gravity, and as it collapsed, it heated up. The center eventually got hot enough for nuclear fusion to begin. The star now burns hydrogen, fusing it into helium and releasing tremendous amounts of energy. That energy radiates into space as light and heat, and that radiation carries entropy. The sun increases the universe's total entropy every second it shines. Eventually, the sun will exhaust its hydrogen fuel, expand into a red giant, cast off its outer layers, and leave behind a white dwarf. That white dwarf will slowly cool over trillions of years, radiating its heat into space. More entropy. Every process, every event, every change moves the universe toward higher entropy. You might wonder why the universe started in such a low entropy state. That's one of the deepest mysteries in cosmology. The Big Bang theory describes how the universe evolved from a hot, dense state, but it doesn't explain why that state had such low entropy. Some physicists point to cosmic inflation, a period of exponential expansion in the universe's first fraction of a second, as a possible explanation. Inflation would have smoothed out most irregularities, creating a universe that looks the same in all directions, which is a low entropy configuration when gravity is involved. But this just pushes the question back a step. Why did inflation happen? What caused the conditions that led to inflation? We don't have good answers yet. What we do know is that the universe started with low entropy and has been increasing its entropy ever since. Stars form and die. Black holes grow and evaporate. Galaxies merge and disperse. Every process increases entropy. And here's the crucial point. This process has a direction but no endpoint except maximum entropy. Once the universe reaches maximum entropy, once all available energy has been distributed as evenly as possible, once all temperature gradients have been eliminated, no more work can be done. No more interesting processes can occur. You've reached heat death. The universe achieves equilibrium, and equilibrium, in thermodynamic terms, means death. Some people find this profoundly depressing. The idea that everything we do, everything we create, every relationship we form, every discovery we make, All of it moves us one tiny step closer to cosmic heat. Death can feel nihilistic, but I want to offer a different perspective. The fact that the universe started in a low entropy state and is gradually evolving toward high entropy creates a window of opportunity. That window is where we live. That window is where all the interesting things happen. Consider what a high entropy universe looks like. Uniform temperature, no structure, no stars, no planets, no life. Nothing changes because nothing can change. Now consider what a maximum low entropy universe would look like. All matter compressed into a single point. Also no structure, no stars, no planets, no life. The interesting stuff, the complexity, the possibility for consciousness and creativity and love, all of that exists in the middle ground, in the zone between perfect order and perfect chaos, between minimum and maximum entropy. We exist in that zone right now, in this brief cosmic moment when the universe has expanded and cooled enough to allow complexity, but hasn't yet expanded and cooled so much that complexity becomes impossible. Life itself represents an entropy reduction machine, but only locally and temporarily. When you eat food, your body breaks down complex molecules into simpler ones, extracting energy to power your cells, your thoughts, your movements. That process increases entropy overall, even though it maintains the low entropy structure of your body for a while. Eventually you'll die, and your body will decay, and all that carefully maintained structure will dissolve back into the environment. The atoms that made up your body will scatter. Some will become part of other organisms. Some will sink into the earth. Some will drift in the air. Your personal entropy will increase to match the universe around you. This happens to everyone and everything. Stars, planets, galaxies, all temporary decreases in entropy in a universe trending inexorably toward maximum disorder. But temporary doesn't mean meaningless. A sunset is temporary, lasting perhaps 30 minutes from start to finish, but we still find it beautiful. A piece of music is temporary, existing only while it's being performed or played, but we still find it moving. Life is temporary, lasting perhaps 80 years if you're lucky, but we still find it valuable. The temporary nature of something doesn't diminish its significance. If anything, it enhances it. A sunset wouldn't be beautiful if it lasted forever. Music wouldn't be moving if it never ended. Life wouldn't be precious if we had infinite time to live it. The universe's eventual heat death operates on the same principle, but scaled up to cosmic proportions. The entire universe exists in a temporary state between its low entropy beginning and its high entropy end. During that temporary window, stars shine, planets form, life emerges, consciousness develops. That window lasts trillions of years, far longer than any human lifetime, but it's still temporary, and perhaps that's okay. Perhaps the point is to experience and appreciate the window while we're in it, rather than mourning its inevitable close. Let me tell you about something called Boltzmann brains. This concept comes from the Austrian physicist Ludwig Boltzmann, who made fundamental contributions to thermodynamics and statistical mechanics in the late 19th and early 20th centuries. Boltzmann understood that the second law of thermodynamics is statistical rather than absolute. When we say entropy always increases, we really mean it almost always increases. There's a tiny probability that entropy could spontaneously decrease through random fluctuations. For example, all the air molecules in a room could, by sheer chance, all move to one corner simultaneously, creating a vacuum in the rest of the room. The probability of this happening is unimaginably small, but it's not exactly zero. Boltzmann realized this has strange implications for a universe approaching heat death. In a maximum entropy universe, you'd expect random fluctuations to occasionally create pockets of lower entropy. Given infinite time, these fluctuations could create anything, including structured matter or even conscious observers. But here's the problem. The most probable fluctuation that creates a conscious observer isn't a fluctuation that creates an entire planet with billions of years of evolution leading to that observer. The most probable fluctuation is one that creates just the observer's brain, complete with false memories and sensory experiences, that pops into existence for a moment and then dissolves back into chaos. A Boltzmann brain. If you wait long enough in a heat-death universe, Boltzmann brains should vastly outnumber real observers that evolved through normal processes. This creates a paradox. If most observers in the universe are Boltzmann brains with random false memories, then you should expect to be a Boltzmann brain. But Boltzmann brains would have random experiences that don't follow consistent laws of physics. The fact that our universe does follow consistent laws, that we can make predictions and have them come true, suggests we're probably not Boltzmann brains. But if we're not Boltzmann brains, and if the universe eventually reaches heat death and stays there forever, then Boltzmann brains will eventually outnumber real observers by an astronomical margin. This creates a probability problem that cosmologists still debate. Some physicists use this paradox to argue that the universe can't reach heat death and stay there forever. Maybe something happens at maximum entropy that resets the cosmic clock. Maybe our universe is part of a larger multiverse where new universes are constantly being created. Maybe the laws of physics change in ways we don't understand at extreme timescales. Or maybe the Boltzmann brain paradox reveals a flaw in our reasoning about probability and cosmology. We don't have a clear resolution yet, but the paradox highlights how thinking about the far future of the universe raises deep questions about probability, observation, and the nature of consciousness itself. I want to shift gears and talk about something that might sound like science fiction, but is actually serious physics: the possibility that advanced civilizations could influence or even prevent the universe's heat death. This enters the realm of speculation, but it's speculation grounded in real physics. If civilization persists for millions or billions of years, advancing technologically far beyond anything we can currently imagine, what might be possible? The physicist Freeman Dyson published a paper in 1979 exploring whether life could survive indefinitely in an expanding, cooling universe heading toward heat death. He concluded that it might be possible, but with significant caveats. As the universe expands and cools, less energy becomes available. Any civilization trying to survive would need to slow down its metabolism, thinking more slowly, using less energy, hibernating for longer and longer periods. Dyson calculated that by carefully managing energy resources and accepting longer and longer intervals between thoughts or actions, a civilization could theoretically persist forever, even as the universe approaches heat death. But it would be a strange existence, with conscious moments separated by eons of hibernation. Other physicists have proposed more ambitious ideas. The physicist Frank Tipler suggested that a sufficiently advanced civilization might be able to manipulate the geometry of space-time itself, creating what he called an omega point at the end of time. This omega point would be a region of infinite computational capacity where consciousness could continue indefinitely despite the universe's physical death. The idea requires technologies that border on magic from our current perspective, and most physicists are skeptical, but it shows how thinking about the end of the universe pushes us to consider the ultimate limits of what physics allows. What about preventing heat death entirely? Could a civilization gather enough energy, manipulate space-time in the right ways, and somehow reset the cosmic clock? Perhaps by creating a new Big Bang within the dying universe. The energy requirements would be staggering, far beyond anything we can currently comprehend. You'd need to collect and concentrate energy on scales comparable to the entire observable universe. The technological challenges would make building a Dyson sphere around a star look like stacking children's blocks. And even if you could gather that much energy, the physics of creating a new universe remains purely theoretical. We don't know if it's possible. We don't know what would happen if you tried. You might just create a black hole, or trigger vacuum decay, or nothing at all. But let's entertain the idea for a moment. Imagine a civilization billions of years from now, watching the last stars die, the last black holes evaporate, facing the approaching darkness of heat death. They've had eons to advance their technology and understanding. They've spread across millions of galaxies, harvesting energy from every available source. They've developed computers that span solar systems, able to simulate entire universes in their calculations. They've probed the deepest laws of physics, understanding quantum gravity and the fundamental nature of space-time. With all this knowledge and power, they attempt to prevent heat death. Maybe they succeed. Maybe they find a way to channel energy in ways that locally reverse entropy. Maybe they create stable pockets of low entropy that persist even as the rest of the universe dies. Maybe they punch through to a younger universe or create a new one entirely. Or maybe they fail. Maybe the laws of physics simply don't allow for what they're trying to do. Maybe heat death, like mortality for individuals, represents an inescapable fact of existence. We can't know from our current vantage point, but the fact that we can even conceive of such possibilities shows how far human thought has come. Here's something that might surprise you about the end of the universe. We've actually observed pieces of it already. When astronomers look at the most distant galaxies, they're looking billions of years into the past because light takes that long to reach us. The most distant galaxy ever observed, currently called HD1, sits approximately 13.5 billion light-years away. We're seeing it as it existed just 300 million years after the Big Bang. That galaxy is long gone by now, evolved into something else, or perhaps merged with other galaxies. We're looking at cosmic history, frozen in light, but we're also looking at cosmic future. The expansion of the universe means that distant galaxies are moving away from us. The farther away a galaxy is, the faster it recedes. At some distance, galaxies recede faster than light can travel through space. Those galaxies have crossed beyond our cosmic horizon. Their light will never reach us. As dark energy continues to drive accelerated expansion, this horizon shrinks. Galaxies that we can see today will disappear beyond the horizon horizon in the future. In roughly 100 billion years, every galaxy outside our local group will have receded beyond the cosmic horizon. An observer in the Milky Way at that time would look out and see a universe containing only the local group galaxies, mostly merged into one giant elliptical galaxy. The rest of the universe would be invisible, not because the stars went out, but because space expanded too fast for their light to reach us. This creates a strange situation for future astronomers. Imagine a civilization that emerges in 1 trillion years, long after most stars have died, but while a few red dwarfs still shine. These astronomers would look at the night sky and see only their local galaxy, no distant galaxies, no cosmic microwave background radiation, because that would have red-shifted beyond detectability. No evidence of the Big Bang, no evidence that the universe is expanding. They would have no way to discover most of what we know about cosmology. Their entire universe would appear to be one static galaxy surrounded by empty space. They wouldn't be wrong exactly. They'd just have access to less information than we do because of when they evolved. This raises an unsettling question. What are we missing? What evidence has already disappeared beyond our cosmic horizon? What crucial information about the universe's origin or fate existed in the past, but is now lost to us forever? We assume we can see enough of the universe to understand its fundamental nature, but that assumption might be flawed. There could be structures or processes occurring beyond our horizon that completely change the picture. We're like fish in a pond, unable to see the ocean beyond, assuming our pond represents all there is. The cosmic horizon demonstrates something profound about information and entropy. Information can be destroyed. Once a galaxy crosses beyond our horizon, any information it carried becomes inaccessible to us. That information still exists in some sense, but we can never retrieve it. Black holes do something similar, but more extreme. Anything that falls into a black hole takes its information with it beyond the event horizon. For decades, physicists thought this information was lost forever, which seemed to violate quantum mechanics. Stephen Hawking's famous black hole information paradox pointed out this contradiction. If black holes destroy information, and black holes eventually evaporate through Hawking radiation, then information has been permanently erased from the universe, which quantum mechanics says shouldn't be possible. Recent work by physicists, including Hawking himself before his death in 2018, suggests the information might not be lost after all. It could be encoded in the Hawking radiation itself in incredibly subtle ways, or it might be stored on the event horizon in a holographic manner. The details get deeply technical, involving quantum field theory in curved space-time and string theory. But the core point is this: the universe seems to preserve information even when it appears to be destroying it. This principle, called unitarity in quantum mechanics, might be fundamental to how reality works. Information can be scrambled, encrypted, made inaccessible, but not truly destroyed. Heat death represents the ultimate scrambling of information. All the structure, all the patterns, all the complexity gets spread out uniformly across an enormous volume of space. The information about how things used to be still exists in principle, encoded in the positions and momenta of all the particles, but it's so thoroughly mixed that extracting any meaningful pattern becomes impossible. It's like taking all the books ever written, grinding them into molecules, and scattering those molecules across the solar system. The information is still there, but good luck reading any books. Let me tell you about proton decay, because it matters for how heat death plays out. Protons, the positively charged particles in atomic nuclei, appear to be stable. An isolated proton, as far as we can tell, lasts forever. We've never observed a proton decay. But some theories in particle physics, particularly grand unified theories that attempt to unify the electromagnetic, weak and strong forces, predict that protons should eventually decay with an extremely long half-life. Current experiments have set the lower bound on the proton half-life at approximately 10 to the 34 years. That means if you watch 10 to the 34 protons for a year, you'd expect to see about half of them decay. If protons do decay, even with such enormous half-lives, it changes the timeline for heat death. Remember those black dwarfs, the cold remnants of white dwarfs I mentioned earlier? If protons decay, then black dwarfs won't last forever. Over timescales of 10 to the 37 or 10 to the 40 years, the atoms in a black dwarf would decay, converting the entire object into radiation. The same thing would happen to any neutron stars, planets, or other matter still around. Matter itself would dissolve, leaving only photons, leptons, and maybe dark matter particles if those are stable. This would happen long before black holes finish evaporating through Hawking radiation. So in a universe with proton decay, the matter era ends much sooner than in a universe without it. it. We don't know whether protons decay or not. Experiments are ongoing, deep underground, in mines and tunnels shielded from cosmic rays. Massive tanks of pure water sit surrounded by detectors, waiting to catch the telltale signal of a proton decaying. So far, nothing. But the absence of evidence isn't evidence of absence when you're looking for processes with half-lives longer than the current age of the universe by factors of trillions. We might need to wait decades or centuries of observation time with ever larger detectors before we see a decay, or we might never see one because protons are truly stable. Either result would tell us something fundamental about the laws of physics. The question of proton stability connects to deeper issues about the fundamental forces of nature. We currently understand physics through what's called the Standard Model, a theory that describes how elementary particles interact through three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity, the fourth force, is described separately by general relativity. The Standard Model has been enormously successful. Every prediction it makes has been confirmed by experiment, including the discovery of the Higgs boson in 2012. But physicists know the Standard Model is incomplete. One problem is that the Standard Model contains about 20 free parameters, numbers that have to be measured experimentally rather than predicted by the theory: the mass of the electron, the strength of the electromagnetic force, the mass of quarks, and so on. Why do these parameters have the values they do? The Standard Model can't answer that question. Another problem is that the Standard Model doesn't include gravity. At low energies, this doesn't matter much. Gravity is so weak compared to the other forces that you can usually ignore it when dealing with elementary particles. But at very high energies, like those present in the early universe or near black hole singularities, quantum effects of gravity become important. We need a theory of quantum gravity, and we don't have one yet. Grand unified theories attempt to unify the electromagnetic, weak, and strong forces into a single force that operated in the very early universe when temperatures were extremely high. As the universe cooled, this unified force split into the separate forces we observe today, similar to how water vapor condenses into liquid water when it cools. If grand unification is correct, it would reduce the number of free parameters in our theories and provide a more elegant description of nature. But it would also predict proton decay. Different gut models predict different proton lifetimes, but most are in the range of 10 to the 34 to 10 to the 36 years. So far, experiments haven't found any evidence for proton decay, which rules out some simpler gut models but leaves others viable. String theory represents another attempt to go beyond the Standard Model. String theory posits that the fundamental constituents of reality aren't point particles but tiny vibrating strings of energy. Different vibration modes of these strings correspond to different particles. An electron is a string vibrating one way. A quark is a string vibrating another way. String theory has the appealing feature that it naturally includes gravity. The graviton, the hypothetical particle that carries the gravitational force, emerges as a particular vibration mode of strings. This would unify all four fundamental forces into a single theoretical framework. The problem with string theory is that it makes very few testable predictions at energy scales we can currently probe. Most of string theory's distinctive features only show up at energies near the Planck scale, which is 10 to the 19 GeV. The Large Hadron Collider can reach energies of about 10 to the 4 GeV. We'd need a particle accelerator the size of the solar system to directly test string theory. Without experimental evidence, string theory remains a beautiful mathematical framework that might or might not describe reality. Some physicists have devoted their careers to developing string theory. Others dismiss it as untestable speculation. The debate continues. Why does this matter for the end of the universe? Because the correct theory of quantum gravity and particle physics at the highest energies determines crucial details about cosmic fate. Does proton decay occur? Is the vacuum truly stable or only metastable? Are there other fields or particles that affect dark energy? Can information be truly destroyed, or is it always preserved? We can't answer these questions definitively without a complete theory of physics. So when we talk about heat death or the Big Rip or vacuum decay, we're making predictions based on our current understanding, which we know is incomplete. Future discoveries could change the picture significantly. Let me paint a different kind of scenario for a moment, one that's more speculative but grounded in real physics. Suppose the vacuum decay calculation is wrong, not because our measurements of the Higgs mass are incorrect, but because there's some new physics we haven't discovered yet that stabilizes the vacuum. Maybe there's a hidden sector of particles that don't interact with normal matter except through gravity and the Higgs field. Maybe dark matter particles have properties that affect vacuum stability. We detect dark matter's gravitational effects, but we don't know what it's made of. The leading candidates are weakly interacting massive particles, or WIMPs, but decades of experiments have failed to directly detect them. Dark matter could be something completely different, and that something might change the vacuum stability calculation. Or suppose dark energy isn't constant. Right now, measurements suggest dark energy has an equation of state parameter very close to -1, which corresponds to a cosmological constant, a property of space itself. But what if dark energy is actually a dynamic field, something called quintessence, that evolves over time? Depending on how quintessence evolves, it could lead to outcomes different from simple heat death. Some quintessence models allow for a bouncing universe, where expansion eventually reverses, leading to a big crunch, followed by another big bang. Cyclic or ekpyrotic universe models explore this possibility. We'd live in one cycle of an eternally recurring cosmos. The Big Crunch was actually the favored model for the universe's end before the discovery of dark energy in 1998. If the universe contained enough matter, gravity would eventually overcome the expansion and pull everything back together. The universe would collapse, galaxies merging, space contracting, temperatures rising. Eventually, everything would compress back into an incredibly hot, dense state similar to the Big Bang, but in reverse. Some models suggested this could trigger a new Big Bang, creating a cyclic universe that expands and contracts eternally. Each cycle would erase most information from the previous cycle, so each universe would be essentially new. The discovery that expansion is accelerating killed most Big Crunch scenarios. You need dark energy to be negative or decreasing over time for gravity to eventually win, and observations suggest the opposite. Dark energy appears to be positive and possibly constant, but we can't completely rule out the possibility that dark energy might change in the future. If dark energy decreased significantly over the next trillion years, a big crunch could still happen. We just have no evidence that it will, and considerable evidence that it won't. There's something poetic about the big crunch, though. The universe would die in fire rather than ice, in compression rather than expansion. Everything would come together in a final apocalyptic convergence. T.S. Eliot wrote, "This is the way the world ends, not with a bang, but with a whimper." Heat death follows Eliot's vision, but the big crunch would be exactly a bang. The loudest possible bang. Both endings lead to the same place, though, the end of everything we know. Whether the universe ends in fire or ice, in maximum entropy or maximum compression, the result for us is the same. We won't be around to see it either way. I want to take a moment to talk about time scales and human intuition, because I think this is where our minds start to fail us when contemplating the end of the universe. We evolve to think in terms of days, seasons, and lifetimes. A human lifetime of 80 years feels long to us. 1,000 years, the span from the Middle Ages to now, feels ancient. 1,000,000 years, the rough time span of human evolution from Homo erectus to modern humans, feels almost incomprehensible. But 1,000,000 years is nothing on cosmic scales, absolutely nothing. The universe is currently 13.8 billion years old. That's 13,800 million years. The sun will continue burning for roughly another 5 billion years before expanding into a red giant and consuming the inner planets. 5 billion years exceeds the entire history of Earth's existence so far. The last stars, those dim red dwarfs we discussed earlier, will burn for 10 trillion years. That's 10 million years. 10 million sets of 1,000,000 years each. Your brain cannot truly comprehend this number. Neither can mine. We can write it down. We can do mathematics with it, but we cannot feel it in any meaningful way. And yet 10 trillion years represents just the opening act of the universe's story. Heat death occurs around 10 to the 100 years in the future. That's a 1 followed by 100 zeros. If you tried to count to that number, counting one number per second, never sleeping, never stopping, it would take you roughly 10 to the 92 years just to count that high. The heat death of the universe would happen long before you finished counting. The number is so large it loses meaning. It becomes abstract, a mathematical symbol rather than a quantity we can grasp. Why does this matter? Because when we talk about the universe ending in heat death, or through vacuum decay, or in a big rip, we're discussing events separated from us by timescales that make our entire existence, the entire existence of our species, the entire existence of life on Earth, seem like less than an eye blink. From the universe's perspective, if the universe could have a perspective, the difference between you being born and you dying is essentially zero. The difference between the first humans emerging and the last humans dying out is essentially zero. All of human history, from the first cave paintings to the last starship, compresses into a moment too brief to measure against cosmic time. This realization can feel depressing or liberating, depending on your philosophical orientation. Some people find comfort in cosmic insignificance. If nothing we do matters on universal scales, then we're free to create our own meaning without worrying about cosmic judgment or consequences. Others find this perspective nihilistic. If everything ends and nothing lasts, why bother doing anything at all? Why create art, pursue knowledge, love each other, if entropy will eventually erase all trace of it? The philosopher Thomas Nagel wrote about what he called the absurd, the fundamental disconnect between humans' search for meaning and the universe's apparent meaninglessness. We want our lives to matter, to have significance beyond ourselves, but we live in a universe governed by impersonal physical laws that don't care about human values or aspirations. The universe doesn't care whether you're kind or cruel, creative or destructive, because the universe doesn't care about anything. Caring is something minds do, and minds are temporary local phenomena in a universe that's mostly empty space. But Nagel argued that recognizing this absurdity doesn't require despair. We can acknowledge that the universe doesn't provide inherent meaning while still creating meaning within our own lives and communities. Meaning doesn't have to be cosmic to be real. The love you feel for your family, the satisfaction you get from work well done, the beauty you find in music or nature, all of these are real and meaningful, even though they're temporary and local. A sunset doesn't stop being beautiful just because it only lasts 30 minutes. Your life doesn't stop mattering just because it only lasts 80 years. The physicist Carlo Rovelli has written eloquently about time and meaning in a universe without permanent structures. Rovelli points out that we are time-bound creatures living in a time-bound universe. Everything that exists in time, changes over time, and will eventually cease to exist. But this temporality doesn't diminish reality. The fact that flowers bloom and then wither doesn't make them less real while they bloom. The fact that humans live and then die doesn't make their lives less real while they live. Reality consists of processes unfolding in time, not eternal, unchanging substances. Once you accept this, the temporary nature of everything becomes less threatening and more simply descriptive of how things are. Different cultures and philosophical traditions have developed various responses to mortality and impermanence. Buddhism, particularly in its Tibetan forms, emphasizes the impermanence of all phenomena. Nothing lasts, everything changes. Attachment to permanence causes suffering. The solution is to accept impermanence fully, to appreciate things as they are without clinging to them. When you truly internalize that everything is temporary, you can experience the present moment more fully rather than constantly grasping at the past or worrying about the future. Ancient Stoic philosophy developed a similar approach. The Stoics recognized that most things lie outside our control. You can't control when you die, when the people you love die, when civilizations rise or fall, when the universe ends. You can only control your own thoughts and responses. The Stoic solution is to focus entirely on what's within your control, your character and choices, while accepting everything else with equanimity. The universe will do what it does. Your job is to live virtuously while you can. Existentialist philosophers like Jean-Paul Sartre and Albert Camus grappled with meaning in a universe without God or inherent purpose. Camus famously used the myth of Sisyphus, condemned to roll a boulder up a hill for eternity, only to have it roll back down, as a metaphor for human existence. We're all pushing boulders uphill, doing tasks that ultimately lead nowhere, in a universe that offers no ultimate reward or meaning. But Camus argued we can imagine Sisyphus happy. The struggle itself, the act of pushing the boulder, the defiance of doing it anyway despite the absurdity, creates meaning. We must imagine ourselves happy, even in a meaningless universe. I bring up these philosophical perspectives because discussions about the end of the universe inevitably raise questions about meaning and purpose. If the universe ends, if everything we do gets erased by entropy or consumed by vacuum decay, or torn apart in a big rip, does anything matter? The philosophical traditions I've mentioned suggest various answers, but they all share a common theme. Meaning comes from within, from our choices and experiences and relationships, rather than from eternal cosmic significance. The universe doesn't need to last forever for our lives to matter now. Let me tell you about something called deep time, a concept developed by geologists in the 18th and 19th centuries as they began to understand how old the Earth really is. Before modern geology, most people in Western cultures believed the Earth was only a few thousand years old, created in essentially its current form. Then geologists started examining rock layers, fossils, and geological processes. They realized that mountains take millions of years to form and erode. Rock layers accumulate over vast spans of time. The Earth must be incredibly ancient, far older than human civilization or even human existence. This revelation profoundly disturbed many people at the time. It displaced humans from the center of creation's timeline. We weren't there at the beginning. We arrived late, after the planet had already existed for billions of years, after countless species had evolved and gone extinct, and we would likely disappear long before the planet's story ended. This realization that human existence occupies just a tiny sliver of Earth's history felt diminishing to many people. We're not the main characters in Earth's story. We're barely a footnote. But geologists developed a way of thinking about deep time that acknowledges human insignificance while still finding wonder in it. John McPhee, in his book Basin and Range, describes placing his arms along a timeline with one hand representing the Big Bang and the other representing now. The distance from fingertip to fingertip represents all of cosmic history. On this scale, all of human history could be erased with a single stroke of a nail file on the fingernail of the outermost hand. We occupy almost no time at all, yet here we are, conscious and thinking and wondering about our place in the vastness. That's remarkable in itself. Deep time teaches humility, but also perspective. Yes, we're insignificant against the backdrop of billions of years, but insignificance doesn't mean worthlessness. An individual atom is insignificant in a human body, yet remove all the atoms and there's no body. Every part of the universe, no matter how small or brief, is part of the whole. You're made of atoms that were forged in stars billions of years ago. Those atoms will continue existing long after you die, becoming part of other structures, other processes. You're not separate from the universe. You're a temporary pattern that the universe has formed, a way that matter and energy have organized themselves for a brief time before reorganizing into something else. The astronomer Carl Sagan captured this beautifully in his Cosmos series. He described humans as a way for the cosmos to know itself. The atoms in your brain emerged from the Big Bang, formed in stars, scattered across space, eventually coalesced into the solar system and Earth, became part of living organisms through billions of years of evolution, and now comprise a structure complex enough to contemplate its own origins. The universe produced you, and you are now thinking about the universe. That recursive loop, that self-reflection, seems almost miraculous. Whether it has cosmic significance or not, it has significance to us. Here's another way to think about our place in time. Imagine the entire history of the universe as a mountain range. The Big Bang is the first peak. The present moment is somewhere in the middle range. Heat death is the last peak, so far away you can barely see it through the atmospheric haze. Now imagine you're standing on one particular mountain in this range, the mountain representing the current epoch. Behind you are countless mountains representing the past. Ahead of you are countless mountains representing the future. You can only stand on one mountain at a time. You can only exist in one moment, but that moment is real. The mountain you're standing on is solid ground. The fact that there are other mountains before and after doesn't make your mountain less real or less worth experiencing. Every conscious being that has ever existed or will exist faces the same situation. They exist in their moment, on their mountain, experiencing the universe from their particular perspective. A dinosaur experienced the late Cretaceous period 65 million years ago. You're experiencing the early 21st century. Beings billions of years in the future, if any exist, will experience their time. None of these perspectives is more or less valid than the others. All are equally real to those experiencing them. Time flows forward, but every moment is equally present to those within it. This connects to what physicists call the block universe interpretation of time. In relativity theory, space and time are united into a four-dimensional space-time. The past, present, and future all exist equally within this four-dimensional block. We experience time as flowing, as a river carrying us from past to future. But that's a feature of our consciousness rather than a fundamental property of reality. From a physics standpoint, all of space-time exists at once. The moment you were born and the moment you die, and every moment in between are all equally real, all equally part of the space-time block. If the block universe interpretation is correct, then in some sense nothing ever truly ends. Everything that happens continues to exist timelessly as part of the four-dimensional structure of space-time. Your life, your experiences, your consciousness at every moment all remain eternally embedded in the space-time fabric. They don't cease to exist when you die any more than last year ceases to exist when this year begins. They remain part of the structure, timelessly existing in their particular location in space-time. This offers a strange kind of immortality, very different from the traditional idea of living forever but perhaps more physically grounded. Let me shift focus to something that might sound like science fiction but emerges directly from serious physics. What happens to consciousness as the universe dies? We've talked about matter dissolving, stars dying, black holes evaporating. But what about minds? What about intelligence, awareness, the subjective experience of being? If advanced civilizations exist millions or billions of years from now, as the universe approaches its end, what options would they have? Could consciousness itself find a way to persist through heat death or survive vacuum decay? The physicist Freeman Dyson explored this question in a paper published in Reviews of Modern Physics in 1979. Dyson asked whether life could continue indefinitely in an open universe expanding forever toward heat death. His answer, surprisingly, was maybe, but the requirements would be extraordinary. As the universe expands and cools, less and less energy becomes available for doing anything, including thinking. Any civilization hoping to survive would need to slow its metabolism drastically, think fewer thoughts per unit time, hibernate for longer periods between brief moments of activity. Dyson calculated that by carefully managing energy resources and accepting exponentially longer hibernation periods, a civilization could theoretically have an infinite number of subjective experiences even as objective time stretched toward infinity. The trick involves digital consciousness. If minds could be transferred to computers, those computers could be powered down during hibernation and powered up only occasionally to think a few thoughts, then powered down again. As available energy decreased, hibernation periods would lengthen. You might think one thought, then hibernate for 1,000,000 years, think another thought, hibernate for 1,000,000,000 years. From your subjective perspective, you'd be thinking continuously. From an external perspective, you'd be thinking infinitely slowly. This scenario has some beautiful mathematical properties, but faces enormous practical problems. First, you need to solve the consciousness upload problem. Can minds be transferred to computers at all? We don't know. Consciousness remains deeply mysterious. We can't even agree on what it is, let alone how to transfer it to silicon. Second, you need computers that can function at arbitrarily low temperatures, approaching absolute zero. Current computers require some minimum energy to operate and generate waste heat. As the universe cools, maintaining the temperature difference needed for computation becomes increasingly difficult. Third, you need to avoid proton decay, cosmic ray damage, quantum tunneling errors, and countless other potential sources of information loss over timescales of trillions of years. But let's suppose an advanced civilization somehow solves all these problems. They've digitized consciousness, built ultra-low-power quantum computers, developed error correction that works over geological timescales. They implement Dyson's scenario, thinking progressively slower thoughts as the universe cools and expands. From their perspective, they live forever, experiencing an infinite sequence of thoughts and experiences. But what kind of existence would this be, thinking one thought every billion years? Would that feel like living or like an incredibly attenuated form of death? The philosopher David Chalmers has written about what he calls substrate independence, the idea that consciousness doesn't depend on being implemented in biological neurons. If the same information processing patterns that occur in your brain could be replicated in silicon or quantum computers, or any other physical substrate, that substrate would be equally conscious. Chalmers argues this position, though many philosophers and neuroscientists disagree. But if substrate independence is correct, then digital consciousness is at least theoretically possible. Your mind could be uploaded to a computer and would remain you in any meaningful sense. This raises fascinating questions about identity and continuity. Suppose you create a perfect digital copy of your brain. The copy has all your memories, personality traits, thought patterns, everything that makes you you. Is that digital copy actually you? If the biological you dies and the digital copy continues, have you achieved immortality or just created a copy that thinks it's you while the real you died? Philosophers call this the problem of personal identity, and different theories give different answers. There's no consensus. Some theories emphasize psychological continuity. If the digital copy has continuous memories connecting it back to the biological you, if it experiences itself as being you, then it is you in any meaningful sense. Other theories emphasize physical continuity. The atoms in your body now aren't the same atoms that were there 7 years ago. Cells die and are replaced. Molecules get exchanged with the environment, yet you feel like the same person. Why? Because there's continuous physical overlap. Each moment's body overlaps substantially with the previous moment's body. But uploading breaks that physical continuity completely. The digital copy shares no atoms with the biological original. Is it still you? I don't have answers to these questions. I'm not sure anyone does. But they become urgently practical if consciousness upload becomes possible, and if civilizations want to survive cosmic timescales. If you can't upload consciousness, then all minds die when their biological or robotic substrates fail. If you can upload but the upload isn't really you, then you still die, even if something that thinks it's you continues. Only if you can upload and the upload genuinely is you does digital immortality work. Here's an even stranger possibility, proposed by the physicist Frank Tipler. Tipler suggested that in the final moments before a big crunch, if the universe were to collapse, the temperature and energy density would approach infinity. This would provide infinite computational resources in a finite time. A sufficiently advanced civilization could, in principle, run an infinite number of computations in the final seconds before the crunch, experiencing an infinite subjective time even though objective time is ending. Tipler called this the omega point and suggested it could serve as a physical basis for concepts like heaven or eternal life. The problem with Tipler's scenario is that we now know the universe probably isn't going to collapse. Dark energy is driving accelerated expansion, not contraction. The Big Crunch looks unlikely, so the omega point probably doesn't exist, at least not in our universe. But the underlying idea remains interesting. If you could somehow access infinite computational resources, you could run infinitely many simulations, experience infinitely many subjective moments, in a sense live forever even in a dying universe. The question is whether such resources exist anywhere, and current physics says probably not. Let's talk about the Fermi paradox in the context of cosmic endings. The Fermi paradox asks why, if the universe is so vast and old, we haven't detected any signs of alien civilizations. Where is everybody? Many solutions have been proposed. Maybe life is incredibly rare. Maybe intelligence is incredibly rare. Maybe civilizations tend to destroy themselves shortly after achieving technology. Maybe they exist but are too far away to detect or communicate with. Or maybe we're actually alone, the only intelligent species in the observable universe. The cosmic ending scenarios we've been discussing add another dimension to the Fermi paradox. Suppose civilizations do arise frequently and do become technologically advanced. Would they stay near their home stars, or would they spread across the galaxy, building Dyson spheres around stars to capture energy, terraforming planets, sending probes and ships in all directions? Most models of galactic colonization suggest that even with slower-than-light travel, a civilization could spread across the entire Milky Way in just a few million years. That sounds like a long time, but represents just a blink compared to the galaxy's age of over 13 billion years. If civilizations typically spread and persist, the galaxy should be teeming with them. We should see evidence of stellar engineering, Dyson spheres blocking starlight, radio transmissions, probes visiting our solar system. We see none of this. Why? One possibility is that civilizations don't persist for millions of years. They emerge, flourish briefly, and vanish, possibly destroying themselves through war, environmental collapse, or technological accidents. If the average civilization lasts only 10,000 years, which is roughly how long human civilization has existed so far, then at any given moment, very few civilizations would be active. Most would have already come and gone, leaving little trace. Another possibility relates to the end scenarios we've discussed. Maybe advanced civilizations look at the physics and realize the universe is doomed. Heat death, vacuum decay, the Big Rip, whatever. Why spread across the galaxy, invest enormous resources in stellar engineering and colonization if everything ends anyway? Maybe civilizations become inward-focused, exploring virtual realities or digital existence rather than physical space. They might create simulated universes inside computers, universes that can be tuned to have properties different from our own, perhaps universes without heat death. This leads to the simulation hypothesis, the idea that we might already be living in a simulated universe created by some advanced civilization. If it's possible to create realistic simulations of universes, and if civilizations routinely do so, then simulated universes would vastly outnumber real universes. By simple probability, we're more likely to be in a simulation than in base reality. The philosopher Nick Bostrom formalized this argument, showing that at least one of three propositions must be true. Civilizations almost never reach the technological level needed to create simulated universes. Civilizations that reach that level almost never choose to run such simulations, or we are almost certainly living in a simulation. If we are in a simulation, does that change anything about cosmic endings? Maybe. The simulated universe might end when the simulation is turned off, regardless of what the physics within the simulation predicts. Or the simulation might be designed to run forever, with the simulators providing computational resources that never run out from the simulation's internal perspective. We'd experience heat death or vacuum decay or whatever our physics predicts, but from outside the simulation, it might just be one program ending and another beginning. These ideas are deeply speculative and arguably unfalsifiable, but they're worth considering when thinking about the ultimate nature of reality and consciousness. Let me bring this back to something more concrete. Whether we're in a simulation or not, whether consciousness can be uploaded or not, whether civilizations spread or stay home, one thing seems clear: we're living in a special time. The universe is currently about 13.8 billion years old. Stars are still forming, galaxies are still merging and creating new structures. Life has had time to evolve on Earth, and presumably on other planets if conditions are right. The universe is old enough to be interesting, but young enough to be full of energy and possibility. This epoch won't last forever. 100 billion years from now, star formation will have essentially ceased. Most stars will be red dwarfs slowly burning their remaining fuel. The universe will be darker, colder, emptier. A trillion years from now, even the red dwarfs will be dying. By 10 trillion years, the stelliferous era, the age of stars, will be over. The universe will enter what cosmologists call the degenerate era, dominated by white dwarfs, brown dwarfs, and black holes. Eventually, even that gives way to the black hole era, and finally the dark era after the last black holes evaporate. We live at the beginning of cosmic history, in the bright, energetic, interesting phase. But here's what I find remarkable. Despite being at the beginning, despite having only 13.8 billion years to work with, the universe has already produced structures complex enough to contemplate their own existence. Stars formed from hydrogen gas, planets coalesced from stellar debris. On at least one planet, probably many more, chemistry gave rise to biology. Biology evolved nervous systems. Nervous systems developed consciousness. Consciousness developed language, culture, science, philosophy. And now consciousness is looking back at the universe that created it and asking how that universe began and how it will end. This seems almost impossibly unlikely. The vast majority of matter in the universe sits in stars or interstellar gas or dark matter halos, completely inert, just following physical laws without any awareness or agency. An unimaginably tiny fraction of matter has organized itself into living, thinking beings. We're incredibly rare, possibly unique in the observable universe, though I doubt that. But rare or unique, we exist. Against tremendous odds, the universe has produced observers. The physicist Paul Davies has argued that the emergence of life and consciousness might be more than just an accident, more than just a lucky fluctuation in a mostly dead universe. Maybe the laws of physics are actually biased toward producing complexity and consciousness. This would require fine-tuning of fundamental constants and initial conditions, which is indeed what we observe. Change the strength of gravity slightly, and stars couldn't form. Change the mass of the electrons slightly, and chemistry wouldn't work. Change the initial density of the early universe slightly, and either everything would have collapsed into black holes, or nothing would have ever come together to form galaxies. The universe we observe sits in a narrow range of parameters that allows for complexity. Why? The anthropic principle provides one answer. We observe these parameters because any universe with different parameters wouldn't produce observers to notice anything. We're selected from the space of possible universes by the requirement that someone exists to ask the question. This explanation feels circular but might be correct, especially if combined with multiverse ideas. If countless universes exist with different physical constants, we necessarily find ourselves in one of the rare universes that allows for our existence. The others exist, but don't produce anyone to wonder about them. Alternatively, maybe there's some deeper principle, some fundamental law we haven't discovered yet, that explains why the constants have the values they do. Maybe the constants aren't actually free parameters, but emerge necessarily from a more fundamental theory. String theory attempts to do this, deriving particle masses and force strengths from the geometry of extra dimensions. But we don't yet know if string theory correctly describes reality. Until we have a complete fundamental theory, the fine-tuning of physical constants remains mysterious. There's something crucial we need to address about everything I've told you so far. All our predictions about the universe's fate, all our calculations about heat death and vacuum decay and the Big Rip, they're based on observations of the observable universe. And the observable universe represents just a tiny fraction of the entire cosmos. We can only see out to a distance of about 46 billion light-years in any direction. That's the cosmic horizon, determined by the age of the universe and the speed of light. Beyond that horizon, light hasn't had time to reach us yet, so we have no idea what's out there. The entire universe could be vastly larger than the observable portion. It might be infinite for all we know, and different regions of this larger universe might have different properties. The dark energy density might vary from place to place. The laws of physics might be different in regions beyond our horizon. We assume the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations. But we can only test that assumption within our observable patch. Everything beyond remains speculation. This means our predictions about cosmic fate apply only to our observable region. Maybe our local patch of universe heads toward heat death, while other regions undergo big crunches or big rips. Maybe the larger universe contains structures and dynamics we can't even imagine because we're trapped inside one small region with a limited view. It's like trying to understand Earth's climate by studying only your backyard. You might learn something about local conditions, but you'd miss global patterns, ocean currents, atmospheric circulation, all the large-scale dynamics that really drive the system. Some versions of eternal inflation theory suggest that different regions of the universe underwent different amounts of inflation in the early moments after the Big Bang. This would create a patchwork cosmos where different patches have different physical properties. The constants of nature, the things like the strength of gravity or the mass of the electron that we think of as universal, might actually vary from region to region. We happen to exist in a region where the constants allow for complexity and life, but other regions might be completely different and completely sterile. If eternal inflation is correct, then in a sense, the universe never ends. Our local patch might undergo heat death, but somewhere else, New patches are constantly inflating into existence, creating new space, new time, new structures. The multiverse as a whole would be eternal and immortal, even though individual regions within it have beginnings and endings. This provides a kind of cosmic immortality, though it doesn't help us personally since we're stuck in our particular patch. Recent observations have started to test some of these ideas. The Planck satellite, which mapped the cosmic microwave background radiation in exquisite detail from 2009 to 2013, looked for signs that our observable universe might have collided with another bubble universe in the distant past. Such a collision would leave a distinctive pattern in the microwave background, a kind of bruise on the sky marking where the two bubbles touched. Planck found no convincing evidence of such collisions, which puts some constraints on eternal inflation models, but it doesn't rule them out entirely. The lack of evidence might just mean we got lucky and didn't happen to collide with any nearby bubbles. The James Webb Space Telescope, launched in 2021, has been observing the most distant and ancient galaxies ever seen, galaxies that existed just a few 100 million years after the Big Bang. These observations are already forcing astronomers to revise theories about how quickly galaxies could form and grow in the early universe. Some of the galaxies Webb has found are larger and more mature than current models predicted they should be at such early times. This might mean we don't fully understand the physics of galaxy formation, or it might mean the early universe had properties slightly different from what we assumed. Every new observation has the potential to surprise us and force us to revise our models. Future observations will continue to refine our understanding. The next generation of gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will detect gravitational waves from much more massive sources than current ground-based detectors can see. LISA might detect gravitational waves from supermassive black hole mergers across most of the observable universe, providing a new window into cosmic history. Future surveys of billions of galaxies will map the large-scale structure of the universe with unprecedented precision, testing theories of dark energy and cosmic expansion. But there are fundamental limits to what we can ever observe. The cosmic horizon will always block our view of the larger universe beyond. Even worse, as dark energy drives accelerated expansion, the horizon shrinks over time. Galaxies currently visible to us will eventually recede beyond the horizon and disappear from view. Far future observers will have access to less information about the universe than we do. In a sense, we're living in a golden age of cosmological observation, with access to cosmic microwave background radiation and distant galaxies that future civilizations billions of years from now will never see. This creates an interesting epistemological problem. How do you do science when crucial evidence is disappearing? How do future astronomers figure out that the universe had a Big Bang origin if the microwave background has redshifted beyond detectability and all the distant galaxies have vanished? They might develop completely different theories based on the limited evidence available to them. Those theories might be logically consistent and match all their observations, but still be wrong because they lack access to the full picture. We might be in a similar position right now. There might be crucial evidence about the universe's nature or fate that existed in the distant past, but has already been lost to us. Maybe the very early universe, in the first tiny fractions of a second after the Big Bang, had properties that would completely change our understanding if we could observe them directly. But we can't. We can only make inferences based on indirect evidence, and those inferences might be missing something fundamental. Quantum mechanics adds another layer of uncertainty to predictions about cosmic fate. Quantum theory deals in probabilities rather than certainties. You can calculate the probability that a particle will be here or there, that a decay will happen or not happen, but you can't predict with certainty what will occur in any individual case. On small scales and short time scales, this probabilistic nature doesn't usually matter much. The probabilities are so extreme that unlikely events effectively never happen. But over cosmic timescales, even incredibly unlikely quantum events can occur. Consider vacuum decay again. The probability of any particular cubic meter of space quantum tunneling to true vacuum in any given year is incomprehensibly small, something like 10 to the negative 100. That means it almost certainly won't happen. But multiply that tiny probability by the number of cubic meters in the observable universe, and by the number of years the universe has existed, and you still get a very small number. Vacuum decay remains incredibly unlikely, but the probability isn't exactly zero. Quantum mechanics says it could happen, right now, in the next second, or never. We can't predict which. This fundamental uncertainty bothers some people. We want the universe to follow deterministic laws, where the future flows inevitably from the past. Quantum mechanics says the universe doesn't work that way at its deepest level. The future is probabilistic, a branching tree of possibilities rather than a single determined path. We can calculate the probabilities of different branches, but we can't say with certainty which branch will actually occur until it does. The many worlds interpretation of quantum mechanics takes this even further, suggesting that all possible quantum outcomes actually happen in different branches of reality. Every time a quantum measurement occurs with multiple possible outcomes, the universe splits into multiple copies, one for each outcome. In some branches, you're reading these words right now. In other branches, you decided not to. In some branches, vacuum decay occurred 1 billion years ago and we never existed. In other branches, the universe is stable and heat death awaits. All these possibilities are equally real in different branches of the quantum multiverse. If many worlds is correct, then asking about the fate of the universe becomes a different kind of question. There isn't one fate, but many fates occurring simultaneously in different branches. Some branches head toward heat death, others toward vacuum decay, still others toward scenarios we haven't even considered. You personally exist in one branch and will experience whatever happens in that particular branch. But other versions of you in other branches experience different outcomes. The universe as a whole, encompassing all branches, never ends because there are always branches that continue existing. Most physicists find many worlds philosophically troubling despite its mathematical elegance. It requires accepting the existence of countless unobservable parallel universes, which feels extravagant. But the alternative interpretations of quantum mechanics have their own problems. The Copenhagen interpretation says that quantum systems exist in superpositions of multiple states until measured, at which point they collapse into one definite state. But what counts as a measurement? What causes collapse? These questions remain deeply controversial after nearly a century of quantum mechanics. The point I'm making is that even our most fundamental physics remains incomplete and uncertain. We have theories that work extremely well for describing observations and making predictions. General relativity describes gravity and cosmic expansion with remarkable precision. Quantum mechanics describes the behavior of particles and fields with extraordinary accuracy. The standard model of particle physics has been confirmed by countless experiments. But these theories don't form a complete, unified picture. They contradict each other in certain regimes. They leave questions unanswered. They require approximately 20 free parameters that we have to measure rather than predict. A truly fundamental theory would explain why the universe has the properties it does, rather than just describing those properties. String theory and loop quantum gravity represent attempts to develop such a fundamental theory, but both remain incomplete and unconfirmed by experiment. We might be decades or centuries away from a complete theory of everything, or such a theory might not exist at all. Maybe reality is fundamentally messy and complicated, not reducible to some elegant master equation. Maybe there are questions that physics simply can't answer, questions that lie forever beyond the reach of scientific investigation. This brings me to something the physicist John Wheeler emphasized late in his life. Wheeler, who worked with Niels Bohr and coined the term black hole, became convinced that consciousness and observation play a fundamental role in physics. Quantum mechanics says that a system exists in superposition until measured. But what happens if nobody ever measures it? Does it remain in superposition forever? Wheeler suggested that the universe requires observers to become definite and real. In his view, consciousness doesn't just passively observe the universe, but actively participates in bringing it into existence. Most physicists consider Wheeler's participatory universe idea too radical and mystical, but it points to genuine puzzles at the intersection of quantum mechanics and cosmology. How did the universe exist before there were any observers? Did it exist in some quantum superposition until the first conscious beings evolved to observe it? If the universe will eventually reach heat death with no remaining observers, does it still exist in any meaningful sense? These questions push against the boundaries of what physics can address and venture into philosophy and metaphysics. Let me tell you about one more recent discovery that affects our understanding of cosmic fate. In 2016, astronomers found something completely unexpected. The star KIC 8462852, also known as Tabby's star, was exhibiting bizarre dimming patterns unlike anything seen before. The star would dim by up to 20% at irregular intervals, far more than any planet passing in front of it could explain. Various natural explanations were proposed: comet swarms, dust clouds, but none fit the data perfectly. Some scientists half-jokingly suggested an artificial megastructure, maybe a Dyson sphere under construction by an advanced civilization. Further observations and analysis eventually found a more mundane explanation involving dust. But the episode illustrates an important point. The universe can still surprise us. We think we understand stellar physics pretty well, but then a star behaves in a way we've never seen before, and we have to expand our models. The same thing could happen with cosmology. We might be surprised by observations that force us to completely revise our theories about dark energy, cosmic expansion, or the universe's ultimate fate. In 2023, the James Webb Space Telescope found galaxies at extremely high redshifts that appeared more massive and mature than cosmologists expected for such early times. Some of these galaxies seem to have formed just 200 million years after the Big Bang, but already contain billions of stars. Current models of galaxy formation struggle to explain how galaxies could grow so quickly. This might require revising our understanding of dark matter, star formation, or even the timeline of the early universe. It's a reminder that cosmology remains an active, evolving field with major questions still unanswered. We've spent most of our time together exploring the physics of cosmic endings, the mathematics of entropy and expansion, the quantum mechanics of vacuum decay. But I want to shift our attention now to a different kind of question. How do we live with this knowledge? How does knowing that the universe will end, whether in heat death or a big rip or vacuum decay, affect how we think about our lives, our choices, our civilizations? This becomes a question for psychology and philosophy rather than physics. Throughout human history, people have grappled with apocalyptic thinking. Ancient mythologies are filled with stories of world endings. Norse mythology describes Ragnarok, a final battle that destroys the cosmos before it's reborn. Hindu cosmology describes cycles of creation and destruction spanning billions of years, remarkably prescient given that these ideas emerged thousands of years before modern astronomy. Christian eschatology envisions an end times when the current world order collapses and something new emerges. These stories reflect a deep human concern with endings and what comes after. What's interesting is that traditional apocalyptic narratives almost always include some kind of renewal or transcendence. The world ends, but something better emerges from the ashes. Ragnarok leads to a new golden age. Hindu cycles of destruction are followed by new cycles of creation. Christian apocalypse leads to heaven and divine judgment. Even secular versions of apocalypse, like nuclear war or climate catastrophe, are often imagined as leading to some kind of rebuilt civilization that learns from past mistakes. We seem psychologically resistant to the idea of permanent, final ending with nothing after. The cosmic endings we've discussed don't offer that comfort. Heat death is genuinely final. The universe reaches maximum entropy and stays there forever. There's no renewal, no cycle, no rebirth, just eternal, unchanging darkness. Vacuum decay is even more absolute. The universe doesn't just die, it gets erased, replaced by something with different physics that can't support life or structure. The Big Rip tears everything apart down to the subatomic level. These endings are cosmologically final in ways that traditional apocalypses never were. How do people react when confronted with this knowledge? Psychologically, there seem to be several common responses. Some people experience what we might call cosmic anxiety, a deep unease about the ultimate meaninglessness implied by heat death. If everything ends, if all traces of human existence will eventually be erased, what's the point of anything? This can lead to nihilistic thinking or depression. Other people respond with what I'd call aggressive presentism, a focus on immediate experience and pleasure precisely because nothing lasts. If the universe is doomed, we might as well enjoy ourselves now, eat, drink, and be merry, for tomorrow we die, and in a trillion years the sun dies too. A third response, which I find more interesting and productive, is what the philosopher Samuel Scheffler calls temporal parochialism. Scheffler argues that most of what we care about already exists within temporal boundaries. You care about your family, your friends, your community, your lifetime projects. These already have natural endpoints. Your parents will die, your children will grow up and move on, you'll retire from your career. Buildings you helped construct will eventually be demolished. Nations you consider permanent will rise and fall. Everything you can directly affect or care about already operates on timescales of decades to centuries at most. The fact that the universe itself ends after trillions or googles of years doesn't actually change the temporal boundaries of your concerns. You weren't worried about humanity 10 billion years ago before we existed. Why worry about humanity 10 Google years from now when we'll certainly be gone regardless of cosmic fate? Scheffler suggests we should focus on the temporal scales where we can actually make a difference and where things genuinely matter to us personally. That's typically decades to perhaps centuries, the lifespan of ourselves and a few generations beyond. There's wisdom in this view, but I also think it misses something important. Humans have always been capable of caring about things beyond our immediate temporal and spatial horizons. We create art and science and philosophy, not just for ourselves, but for future generations. We preserve historical knowledge not just for practical use, but because we think the past matters. We engage in long-term projects like fighting climate change or building institutions meant to last centuries because we care about people we'll never meet living in times we'll never see. This capacity to extend our circle of moral concern across time seems like a distinctive and valuable human trait. So maybe the question isn't whether to care about cosmic timescales, but how to care appropriately. The physicist and philosopher Olaf Stapledon explored this in his novel Star Maker, published in 1937. Stapledon describes a cosmic observer who witnesses the entire history of the universe, from first stars to final darkness. The observer sees countless civilizations rise and fall, struggle and achieve, create beauty and meaning, all of it temporary, all of it eventually consumed by entropy. And yet Stapledon finds this vision ennobling rather than depressing. The temporary nature of things doesn't diminish their beauty or significance while they exist. Think about cherry blossoms, celebrated in Japanese culture precisely because they bloom brilliantly but briefly. The blossoms are beautiful because they're temporary, not despite it. If cherry trees bloomed forever, we'd stop noticing them. The limited bloom season makes each spring special. Similarly, perhaps consciousness and civilization are beautiful precisely because they're temporary phenomena in a universe that's mostly empty space and dead matter. We're like cherry blossoms blooming in cosmic spring, brief but magnificent. The writer Alan Lightman, who trained as a physicist before becoming a novelist, has written movingly about living with cosmic knowledge. Lightman describes feeling overwhelmed when contemplating the vast scales of space and time revealed by modern astronomy. How can an individual human life matter when set against billions of galaxies and trillions of years? But then he describes moments of connection and meaning, watching his daughter learn to swim, listening to Beethoven, observing the way light falls through trees. These moments feel significant and real despite their cosmic insignificance. Maybe both perspectives are valid. We're cosmically insignificant and personally meaningful simultaneously. Different cultures have developed different frameworks for thinking about mortality and impermanence. Japanese culture, influenced by Buddhism, has concepts like mono no aware, which translates roughly as the pathos of things, or sensitivity to ephemera. It describes a bittersweet awareness of impermanence, a recognition that beauty is enhanced by transience, cherry blossoms, autumn leaves, the changing seasons, all beautiful precisely because they don't last. This aesthetic philosophy applies to human life as well. We're beautiful partly because we're temporary. Western culture, particularly in America, often struggles more with impermanence. The American dream emphasizes building something lasting, leaving a legacy, achieving immortality through fame or achievement. When confronted with genuine finality, with heat death or vacuum decay, this orientation toward permanence becomes impossible to maintain. You can't leave a permanent legacy in a universe that's going to end. This can feel more threatening to Western sensibilities than to Eastern ones that already embrace impermanence as fundamental. Indigenous cultures often have cyclical rather than linear conceptions of time. Many Native American traditions view time as recurring patterns rather than a line from past to future. In this framework, endings and beginnings interweave constantly. Death feeds life, destruction enables creation. The linear trajectory toward cosmic heat death might feel alien to these worldviews, but the broader principle that things end and transform might feel more familiar and acceptable. I'm not suggesting any of these cultural frameworks is objectively correct. They're different ways humans have developed for making sense of mortality and change. But they show that cosmic knowledge doesn't determine how we respond to it. We have choices about how to integrate scientific understanding with values and meaning. The physics tells us what will happen. Philosophy and culture help us decide what that means and how to live with it. Let me tell you about an experiment in long-term thinking that might change how we think about cosmic timescales. In 1996, computer scientist Danny Hillis and entrepreneur Stuart Brand founded the Long Now Foundation with an audacious goal to encourage long-term thinking by building a mechanical clock designed to run for 10,000 years. The clock of the Long Now, currently under construction inside a mountain in Texas, uses innovative mechanisms to keep time across millennia. It's designed to be accurate, self-maintaining, and comprehensible to future civilizations that might discover it. 10,000 years might seem arbitrary, but it's roughly the span of human civilization from the first cities to now. Looking forward 10,000 years means imagining a future as distant from us as the invention of agriculture is in the past. The clock serves as a monument to long-term thinking, a reminder that human choices and actions have consequences that ripple forward in time far beyond any individual lifetime. Projects like this help train our minds to think in centuries and millennia rather than just days and years. But 10,000 years remains infinitesimal compared to cosmic timescales. The clock will likely fail long before the sun becomes a red giant in 5 billion years, certainly long before heat death in 10 to the 100 years. So what's the point? The Long Now Foundation would argue that the point is training ourselves to think longer term than we naturally do. Most human institutions, businesses, governments operate on timescales of months to decades at most. Extending that to centuries or millennia represents a radical shift in perspective, even if it's still cosmically brief. Climate change provides a concrete example of why long-term thinking matters. The carbon dioxide we emit today will affect atmospheric composition and global temperatures for thousands of years. Decisions made in this century about fossil fuel use, deforestation, and emissions will determine environmental conditions for hundreds of future generations. Yet our political and economic systems are built around quarterly earnings reports and election cycles. The mismatch between the timescale of the problem and the timescale of our institutions creates massive challenges. Now extend this to even longer timescales. Should humanity invest in becoming a multiplanetary species, establishing colonies on Mars or in orbital habitats? The effort would take centuries and cost trillions of dollars. The benefits wouldn't manifest until long after everyone alive today has died. But spreading to multiple worlds might be crucial for long-term survival, protecting against extinction from asteroid impacts, supervolcano eruptions, or nuclear war. How do we make collective decisions that benefit people who won't exist for hundreds or thousands of years? These questions become even more profound when considering truly cosmic timescales. Should we try to preserve human knowledge and culture in forms that could survive for millions or billions of years? Various projects have attempted this. The Voyager probes, launched in 1977, carry golden records with sounds and images from Earth. They're currently in interstellar space and will continue traveling for billions of years, long after human civilization has ended. The information on those records represents a message in a bottle to the cosmic ocean, likely never to be found, but carrying traces of our existence nonetheless. The Svalbard Global Seed Vault, built into a mountain in Norway, preserves seeds from crops around the world, protected against natural disasters and human conflicts. It's designed to last thousands of years and could help rebuild agriculture after a catastrophe. Similar efforts aim to preserve digital information, DNA sequences, human knowledge in forms that future civilizations or alien discoverers might decode. These projects represent long-term thinking in action, attempts to extend human influence and memory beyond our natural lifespans. But there's something poignant and perhaps futile about these efforts when set against heat death. Even if we preserve information perfectly for trillions of years, even if human descendants or successor species spread across the galaxy and persist for billions of years, eventually the stars will die. Eventually black holes will evaporate. Eventually maximum entropy will be reached. All information, all memory, all trace of anything humanity ever did or thought or created will dissolve into the cosmic background. We can delay this. We can make it take longer, but we apparently can't prevent it, unless. Here's where things get speculative, but interesting. What if we're wrong about something fundamental? What if the universe has exit doors we haven't discovered yet? Theoretical physics allows for some wild possibilities that might, just might, offer escape routes from cosmic doom. Wormholes, if they exist and can be stabilized, might connect different regions of space-time, or even different universes. If you could travel through a wormhole to a younger universe, or a universe with different physics, you might escape heat death in your original universe. The mathematics of general relativity permits wormholes in principle, but making them traversable would require exotic matter with negative energy density. We don't know if such matter exists or can be created. Even if it does exist, stabilizing a wormhole large enough for anything bigger than subatomic particles might be impossible. But impossible and proven impossible are different categories. Until we understand physics at the deepest levels, we can't completely rule out the possibility that sufficiently advanced technology might manipulate space-time in ways we currently think are impossible. So we arrive at the end of our journey through cosmic endings. We've explored heat death, the slow fade into eternal darkness. We've examined the Big Rip, where space itself tears apart. We've confronted vacuum decay, the possibility that reality could be erased in an instant. We've discussed the philosophical implications, the uncertainty in our predictions, the limits of our knowledge. Now I want to bring this back to where we started and ask, what does any of this mean for you right now, in this moment? You're listening to these words at a particular time and place. Maybe you're lying in bed, trying to fall asleep. Maybe you're working at your desk and this plays in the background. Maybe you're on a long drive or commute. Wherever you are, whatever you're doing, you exist in the present moment. The heat death of the universe won't happen for 10 to the 100 years. That number is so large it's meaningless to human cognition. For all practical purposes, it might as well be infinite. The Big Rip, if it occurs at all, won't happen for at least 100 billion years. Vacuum decay might happen tomorrow or never. We can't predict it. So what should you take away from all this? Here's what I've come to think after spending years studying cosmology and thinking about these questions. The universe will end. That's almost certainly true. The specific mechanism remains uncertain, but the general principle of ending seems inescapable given what we know about physics. And yet this knowledge changes precisely nothing about how you should live your life today. The ethical obligations you have to other people, the projects that give your life meaning, living, the relationships you value. None of these depend on whether the universe ends in heat death or vacuum decay or something else entirely. When I teach cosmology, students sometimes express existential distress after learning about heat death. They ask, why do anything if it all gets erased eventually? My answer is to question the assumption behind that question. Why would you expect the value of your actions to depend on their permanent cosmic consequences? Does a kind word to a friend matter less because the universe will end in trillions of years? Does creating art or pursuing knowledge become pointless because entropy increases? I don't think so. The meaning and value of human actions come from their effects on conscious beings in the present and near future, not from leaving permanent marks on the cosmos. Think about other things you value that are temporary. A conversation with someone you love matters even though it ends after an hour. A beautiful sunset matters even though it fades after 30 minutes. A good meal matters even though it's consumed and forgotten. Experiences have value independent of their duration. The fact that they end doesn't retroactively erase the meaning they had while occurring. Life works the same way. Your life matters now, to you and to people around you, regardless of what happens to the universe in Googles of years. The philosopher Thomas Nagel wrote something I find helpful here. He said that humans are simultaneously capable of viewing ourselves from a detached cosmic perspective and from an engaged personal perspective. From the cosmic view, we're insignificant specks in an incomprehensibly vast universe, here for an instant and then gone. From the personal view, we're the center of our own experience. Our joys and sufferings are intensely real and important. Both perspectives are valid. The trick is learning to hold both simultaneously without letting either one cancel out the other. You are cosmically insignificant. That's just true. The universe is billions of light years across and will exist for trillions upon trillions of years. Your entire life, from birth to death, occupies less than a single atom's width on the cosmic timeline. Every human civilization from first cities to last starship will compress into a moment too brief to measure. Against that backdrop, you don't matter. Earth doesn't matter. The solar system doesn't matter. And yet, you are also the center of your own conscious experience. Your pain is real. Your happiness is real. Your relationships and choices and experiences are real and matter immensely to you and to people whose lives you touch. How do you reconcile these two truths? I think the answer is that you don't need to. They're both true simultaneously. You can acknowledge your cosmic insignificance while still living a meaningful life. In fact, accepting insignificance might actually be liberating. If the universe doesn't care what you do, if there's no cosmic judgment or ultimate meaning built into reality, then you're free to create your own meaning. You get to decide what matters to you. You get to choose your values, your projects, your relationships. The universe won't validate or invalidate those choices. They're yours to make. This brings me back to the astronomer Carl Sagan, who I quoted earlier. Sagan had a gift for making people feel both small and significant simultaneously. In his pale blue dot speech describing a photograph of Earth taken from 6 billion kilometers away by Voyager 1, Sagan described our planet as a mote of dust suspended in a sunbeam. Everything humans have ever done happened on that tiny pixel. Every war, every romance, every empire and ideology, and moment of triumph or tragedy, all of it on that pale blue dot. Sagan used this cosmic perspective to argue for humility and compassion. We're all on this tiny world together. Our differences seem petty when viewed from space. We should treat each other better. But Sagan also celebrated humanity's achievements. We're the species that figured out where we came from. We decoded our own genetic material. We split the atom. We went to the moon. We sent probes to the edge of the solar system and beyond. We built telescopes that can see nearly to the beginning of time. For a species of barely evolved primates on an average planet orbiting an average star, we've accomplished remarkable things. Yes, we're cosmically insignificant, but we're also conscious, creative, curious beings capable of understanding our own insignificance. That's special even if it's not cosmically important. I want to address one more question that often comes up in discussions of cosmic endings. Should we tell people about this? Is it psychologically harmful to confront the reality of heat death? Would people be happier not knowing that the universe is doomed? Some scientists argue that cosmological nihilism, the sense that nothing matters because everything ends, represents a genuine harm that we should avoid spreading. Maybe we should just not talk about heat death in public, leaving it as technical knowledge for specialists rather than existential burden for everyone. I disagree with this view, though I understand the concern. First, I think people have a right to know what science has discovered about the universe, even if that knowledge is uncomfortable. We don't hide other uncomfortable truths. We tell people that they're mortal, that civilizations rise and fall, that Earth has experienced mass extinctions. Heat death death is just another uncomfortable truth, albeit on a vaster scale. Second, I don't think knowledge of heat death necessarily leads to nihilism or despair. As I've been arguing throughout, you can accept cosmic doom while still finding meaning and purpose in life. Many people do exactly that. Third, and perhaps most importantly, I think confronting cosmic endings can actually be psychologically valuable. It provides perspective. When you realize that the universe will continue for trillions of years after you're gone, that nothing you do will matter on cosmic scales, it becomes easier to let go of petty concerns. Status anxiety, fear of embarrassment, grudges against people who wronged you, all these shrink in importance when viewed against eternity. You might actually become more present, more engaged with immediate experience, more focused on what genuinely matters to you personally rather than what you think you're supposed to care about. The philosopher Stephen Cave, who studies attitudes toward death and immortality, argues that accepting finality is crucial for psychological health. People who cling to fantasies of living forever, whether through religious afterlife or technological immortality or leaving a permanent legacy, often struggle to engage fully with present life. They're always looking ahead to some future state rather than experiencing now, accepting that you will die, that your influence will fade, that even your memory will eventually be lost, allows you to shift focus from the impossible goal of permanence to the achievable goal of living well in the time you have. The same logic applies at cosmic scales, accepting that the universe will end, that all traces of human existence will eventually be erased, frees us from the impossible burden of cosmic significance. We don't need to matter forever. We just need to matter now, to ourselves and each other. That's actually achievable. Cosmic significance isn't. Let me tell you one final story, a thought experiment that brings together many of the themes we've explored. Imagine you're given a choice. Option A, you live a normal human life, 80 years give or take, experiencing all the joys and sorrows that come with human existence. You have relationships, achievements, struggles, moments of beauty and meaning, and then you die, and eventually everyone who knew you dies, and eventually humanity itself disappears, and eventually the universe reaches heat death. Option B, you're uploaded into a computer and live for a Google years, thinking incredibly slowly as the universe expands and cools. You persist until the very last moments before heat death, the final conscious being in existence. But your experience is attenuated, spread thin across impossible timescales. You think one thought every billion years. Which would you choose? When I pose this to people, most choose option A. They'd rather have a rich, intense 80-year human life than a barely conscious Google year existence. Duration doesn't equal value. A brief, intense experience can be more meaningful than an infinitely long but diminished one. This suggests that what we really value is the quality of our conscious experience, not its absolute duration. We want to feel alive, connected, engaged. We want experiences that matter to us subjectively. The cosmic timeline is irrelevant to these values. And maybe that's the ultimate lesson here. The universe will end, but that's a fact about physics, not a fact about meaning or value. Meaning and value come from consciousness, from the subjective experience of beings like us. Physics can tell us what will happen to matter and energy over trillions of years, but physics can't tell us what matters or how to live. Those are questions for human wisdom, philosophy, culture. They're questions we each have to answer for ourselves. So where does this leave us? We've spent 2 hours together exploring the death of the universe. We've looked at the science of cosmic endings, the philosophy of mortality and meaning, the psychology of living with apocalyptic knowledge. We've confronted the fact that everything ends, that heat death or vacuum decay or the Big Rip will eventually erase all structure and complexity from the cosmos. And yet here we are, conscious and thinking, experiencing this moment together. The universe produced us from hydrogen gas and starlight. We've evolved the capacity to understand our own origin and predict our ultimate fate. That's remarkable. Maybe it doesn't have cosmic significance. Maybe it's just a temporary fluctuation in an otherwise dead universe. But it's our fluctuation. We get to experience it, and that's worth something, even if it doesn't last forever. I want to end by asking you a question. After everything we've discussed, after exploring heat death and vacuum decay and the Big Rip, after confronting the evidence that the universe is doomed, what's your response? Does cosmic doom make life feel meaningless or precious? Do you feel despair or liberation, anxiety or peace? There's no right answer. Different people respond differently based on their temperaments, values, and worldviews. But I encourage you to think about it seriously, and I want to hear from you. In the comments, tell me, how does knowing about cosmic endings affect how you think about your life? Does it change anything about how you want to live? What questions do you still have about the fate of the universe? What other cosmic mysteries should we explore together? This journey through the death of the universe has been mine to present, but the meaning we make of it belongs to all of us. We're in this together, for whatever time we have on this pale blue dot suspended in darkness. The universe will die, but right now, in this moment, it's alive. Stars are shining, planets are turning. Somewhere in the cosmos, perhaps on countless worlds, conscious beings are looking up at the night sky and wondering about their place in it all. You're one of those beings. You exist, you're aware, you can think and feel and choose. The fact that it's temporary doesn't make it less real. If anything, it makes it more precious. Every moment of consciousness is a gift, a brief window of awareness in an otherwise unconscious cosmos. Make the most of it while you can. Thank you for taking this journey with me through the end of everything. If you found this exploration meaningful, share it with someone who might appreciate it. Subscribe to join future explorations of cosmic mysteries. And remember, the universe may be doomed, but your life, right now, is yours to shape. Live it well. The cosmos is watching through your eyes.